I'm happy to be moderating the session on satellite data to support emission control strategies. And so at this point, I will ask our first speaker, Annie Anderson from Sonoma Tech, to go ahead and start. And so again, we'll hold questions until the panel discussion at the end.
Good morning, everyone. This is my first in-person HAQAST meeting, so it was very exciting for me to be here. I've attended virtually in the past and learned so much from you folks in other sessions. So it's really an honor for me to be here presenting with you all. And I've learned so much both in the session so far this week and also just talking with you in between. So really happy to be here. The talk I'm going to share with you today is on connecting research to communities using ground and satellite data. I'm here from Sonoma Technology. We are an air quality consulting company based in the San Francisco Bay Area, and I am Annie Anderson. My background is in atmospheric chemistry, and I'm an air quality data scientist at Sonoma Tech. I'm somewhat new to the data science department. I just started at the end of last summer, so I'm definitely still learning, and a big goal of mine being here this week is learning new ways that I could incorporate satellite data into the research and work that I do for our clients. So our clients are pretty varied. This year alone, I've worked with community groups who have an environmental justice grant and are looking for scientific expertise, for government organizations who need research for policy decision-making, and for private companies who need to use our data science and monitoring skills to meet regulatory requirements. So today I'm going to be sharing with you just a few sample projects on how we've integrated satellite data into meeting those needs for our clients. We'll talk about EPA exceptional events, fire growth mapping research, and we don't have too much time for industrial and community monitoring, but I will say a couple words on that. And then I'll wrap up with perspectives on some of the challenges and also growth opportunities for us in using satellite data. So let's jump in with EPA exceptional events. I'm not going to do a ton of background here because I know that there's a ton of expertise in the crowd because I learned so much at the October session that specialized in this, but it is worth saying that exceptional events are extremely critical for community emission control strategies, not only because communities need to know what they can control and what was beyond their control, but also these exceptional events have a strong impact on design values, which then affect NAAQS attainment and the associated federal funding. So we have a team of meteorologists and scientists who do the analysis and submission on behalf of jurisdictions. The examples I'll show you here are for Clark County, Nevada, which includes Las Vegas. And I've got an example of a high wind dust event, as well as wildfires impacting both PM and ozone attainment. The example I've got pulled up for you there is in September 2020, and 2020 was a prolific wildfire year. This is an event of high PM. You can see from the black trace that the PM values exceeded 1,500 micrograms per meter cubed on an hourly basis. And so some of our big questions were, is this maybe a high wind dust event or wildfire impact? So our ground-based data was able to help us with the wind analysis here. We have wind speed on the left and wind trajectories on the right. The wind speeds are in color on the left, and you can see that we had really high wind speeds up to gusts of 50 miles per hour that coincided with the beginning of the PM10 event. And on the right, we saw that the back trajectories of the wind went right through a source region that's very dusty, the Great Basin Desert region. And we were able to look at that and compare it to maybe some potential wildfire areas using satellite data. So we're currently working on the satellite and model analysis. There's a few things that we've included here. One is the MIRA-2 reanalysis data, which helped us see that the wind speeds peaked not only locally in the Las Vegas area, but also in the source region, in the desert region. We also used aerosol optical depth, and you can see here in the dark yellow region that there's a continuous area of high AOD behind the frontal passage. And our area of interest is that black flag there. And I think something that really stands out is that just southwest of our area, there's actually much higher aerosol optical depth in red. And so to further investigate that, we move to the VIIRS true color imagery. And there we see the signature brown-gray mark of wildfire smoke. So we're able to see that the wildfire smoke was not so much impacting our specific region, definitely contributing to regional background PM 2.5 and PM 10 at this time, but the combination of the ground and the satellite data was able to show us that this was most likely a high wind dust event. So the second type of exceptional events that we commonly work on is wildfire influenced ozone. This work is in an exploratory stage. I did a lot of it during my dissertation, and we're just starting to look at incorporating it into exceptional event analysis. For this, we use TROPOMI data, the column formaldehyde and NO2 data, which we use as surrogates for VOCs and NOx. And we take the ratio of the two of them to determine if we are in a NOx limited or a VOC limited regime. So what I am showing you here is 3 maps of California in 3 different months. The colors correspond to those TROPOMI formaldehyde to NO2 ratios. The redder colors are a higher ratio, meaning a more NOx limited environment. The black outlines on the map are the MODIS detected fire perimeters. And so when we compare the TROPOMI ratios to those burned areas, we see 2 really interesting patterns. One is that within the burn area, we see the green color, a decrease in the TROPOMI ratio. And outside of those areas, particularly in October, there's a halo of a redder color, an increased TROPOMI ratio, or a more NOx limited environment outside of that. So what we can see here is that the VOCs from the smoke plume are having a really big impact, particularly outside of the burn area. That's going to have different impacts on ozone production efficiency, depending on where geospatially you're located. So as I mentioned, this is a bit preliminary at this point, so more to come. Stay tuned for any additional insights we have there. The second project I wanted to share with you folks is on wildfire occurrence and growth mapping. It certainly goes without saying that as far as emissions controls, wildfires are one of our biggest problems in the West particularly. So there's a major need for highly resolved spatially and temporally information on wildfire growth progression for both those of us that are here and interested in air quality, but also from the wildfire scientists who want to control fires as well. So for this project, we've partnered with PG&E, which is a utility company in California. And our goal here was to integrate the really fine spatial resolution of VIIRS with the temporal resolution of GOES to better understand fire perimeter growth at sub-daily resolution. So this figure on the right is the MODIS and VIIRS fire detections, really similar to the black outlines on the California maps on the previous slide. And what we want to do is add in that temporal change. So what I'm showing you here is that now in yellow, we have the beginning of the fire in August, and going to the purple period is about 2 months later, and see how those fire perimeters change over time. So the methodology for this work was designed by my excellent colleagues, Dr. Crystal McClure and Nathan Pavlovic. I hope I do them justice in presenting their work today. But their method was to take MODIS and VIIRS satellite fire detections, group them spatially and temporally into individual fire events, shown by their schematic here from their publication. And then they integrated the GOES hourly fire radiative power data. And from that, they calculated sub-daily and daily growth areas and perimeters for each fire event. They used this with data going back to 2003, so they were able to cross-reference that historical fire event with agency records to evaluate the methodology. And that's what this paper citation is here. It just came out in February. So now that we have this methodology, some of our key results are that integrating the GOES fire radiative power data successfully allowed for interpolation of hourly fire growth. And we're able to capture peak daily fire growth periods down to the hour. So the example shown here has the hour since the fire started burning on the x-axis and the percent daily fire growth on the y-axis, showing a peak at about 16 hours into it for these large fires in the 2003 to 2020 period. So to our knowledge, this is the finest resolution quality assured fire growth data set available. So to summarize, we're able to generate fire perimeter data sets of high spatial temporal resolution for fires moving forward as soon as we have that satellite data. And this enables advances in smoke modeling, near-time real fire monitoring, as well as fire behavior and fire weather research efforts and model development efforts. So it's worthwhile to highlight that we have a pipeline set up for this. to be able to get the results turned over within minutes of receiving that satellite data. And if there's a group here who's interested in this type of work, we're happy to put together a proposal, but we don't have a group running this operationally yet. The last topic that we spend a lot of time in is in industrial and community monitoring. I'm kind of limited on time here, and based on my conversations with who's present, I'm going to kind of skip through this one. I do want to say that we do a lot of industrial fence line and community monitoring, particularly focusing on refinery emissions and environmental justice committees or communities. But overall, these are ground-based measurements. What we would ideally like is to have more tiered system where you do have the ground-based measurements, but you can supplement with daily or weekly surveys of for large changes with some sort of airborne or satellite data. Our challenge in this area right now is that most industrial sites that we have are just not large enough for the satellite resolution. So I'm going to wrap up then with a summary of the types of projects we looked at. For exceptional events, we combined ground-based and satellite data to help confirm regional dust events and local meteorology, as well as looking at TROPOMI evaluations for NOx and VOC ratios during ozone events. Some of the growth opportunities that we've seen is that our clients who are working on exceptional events on their own can struggle with the breadth of disciplines and time needed to complete these analyses. That's something that we're kind of able to meet because we do have a large staff. And the second project is wildfire growth mapping, where we integrated the fine spatial resolution of VIIRS with the temporal resolution of GOES to understand fire perimeter growth at sub-daily resolution. Some of our challenges there are that higher frequency is always important for people who need up-to-the-minute updates, particularly in the wildfire science area. And that as far as the satellite data goes, continuing to bring down the spatial resolution is critical. And lastly, I know we just glanced through it, but if anyone has questions, I'm happy to answer. On industrial monitoring, we provide high temporal resolution ground-based monitoring currently, as well as the data management, recording, and communication of that. But we're looking for opportunities to do multi-component monitoring that would add satellite, airborne, or drone measurements. And again, this is another area where continuing to bring down spatial resolution is critical. So with that, I'd like to thank my colleagues, Dr. Crystal McClure and Nathan Pavlovic. Crystal is also the project manager for the exceptional events. He does great work there. And thank you so much for your time. Happy to take any questions.
Great, thank you, Crystal. Sorry, Annie. Thank you, Annie. Okay, so we're going to hold questions until the panel at the end. And so I'm pleased to introduce Benjamin Dufoy from St. Louis University.
Hi, welcome everybody. Welcome to St. Louis. It's a beautiful day to be in St. Louis. It's not always this beautiful, but every season is beautiful, actually. I'm from St. Louis University, which if you go east 4 miles, you will find it there, the first university west of the Mississippi, it turns out. If you keep going another 4 miles, you will hit the river. If you're lucky, you will see wild bald eagles flying around. And I think it's worth remembering this as, you know, we're environmentalists here, that actually we have made tremendous progress. There are these massive successes of air quality. And if you are able to connect with people on this kind of human level, most people will actually agree with you. Yes, this is what we want to do. Sometimes I joke, if somebody thinks the EPA should be scrapped, they should be given a one-way ticket to New Delhi in the winter, or maybe Dhaka, as a month ago, and only be allowed to come back once they've reevaluated their opinions. And I don't mean this as a slam on Delhi or Dhaka. I had a great time visiting, but it would be even better with clean air. So I want to talk about 2 different things to do with emissions and estimating emissions using the TROPOMI satellite. First, we'll talk about TROPOMI NO2. So this is a picture of a Houston of the vertical column density. So you're familiar with this. You can see mainly the ship channel. There we go, poking out in TROPOMI. So this is a big improvement on OMI that would see just this single big blur of pollution over Houston. And you can also kind of guess the highways along here and the urban area. And I've been doing a fair amount of work with the flux divergence method developed by Stefan Böhli in Germany, where you mix this with winds, high resolution winds, to look at what the flux divergence is and ideally find greater detail from this map. And so this is what you get from the same data. And all of a sudden you see that the point source, like this is a big coal power plant. Okay. The parish power plant was kind of a minor blur here. When you do the flux divergence, it really stands out. But you also see some of these other oil facilities here. This is a big refinery over here, all these things that you can start to see all these other point sources and all this detail that shows up doing the flux divergence. The highways show up a little more. And when you're not overlaying it over a map, you can even see a little bit of the airport. So we can do this over different cities. And estimate, do an actual quantitative estimate of the emissions from this. So I did this, I mentioned I was in Dhaka too long ago. Over on the top left, you see the vertical column density, and you see that there is a little bit of structure in that VCD field, but it's mostly uniform. But when you look at the flux divergence, hey, you can start to estimate these different sources. So we do this by doing a Gaussian fit. I'll spare you all the details, they're in the paper over here in Environmental Research Letters. But what's interesting is it's not necessarily, the emissions are not necessarily what we expect, and certainly not what is in the EDGAR inventory. On the bottom left, you have our estimates from TROPOMI. On the bottom right, you have what the EDGAR emission inventory thinks where the NOx is coming from. EDGAR seems to think that these power plants put out a lot of NOx, that light blue circles. And they just don't in reality, or at least in TROPOMI signal, they don't at all. Maybe because these are mixed oil, natural gas plants, and they were operating natural gas at the time. I don't know. But anyway, this is something where the satellite can give direct feedback to the emissions development people. This industrial area here is in EDGAR in smaller areas, but what was surprising to us is the actual urban area of Dhaka is not as big a source as the thing. And then there's this Mauna place here. This is where a lot of our garments are made. We have the shirts in this room, maybe were made over here. It's not at all in the emissions inventory. There are no big sources, and yet somehow it shows up in TROPOMI. So that would be something where the satellites can say, hey, we need to go and see on the ground what is actually happening over there. So we can do this not just for the big cities, you know, Houston, Dhaka, these are the big point sources, and that's what we've traditionally been looking at as satellites, quality scientists, because that's what we see. Here, this is a picture of St. Louis. So a lot of mid-sized cities, you can start to see this kind of resolution. So we're on the edge of the hotspot here in university. You can see St. Louis is still the major kind of source of NOx, but you see the power plants over here, the big Columbia power plant, Wood River Refinery, there's another power plant there show up. But even more than that, what we want to see is we're beginning to see the highways, and St. Charles is an area of big urban growth in St. Louis at the moment, and it really shows up in TROPOMI. So we can start to see all these things. So I want to shift gear now from the NO2 to methane emissions. This is kind of work that happened a little bit serendipitously. My children come back from school and tell me about the scientific method, and it's like, it's like when whoever made a discovery using the scientific method as it's taught in schools. I don't know, maybe you guys do. I think I have an example of my own work. So I wheel out. But I was looking at that and I thought, well, while I'm looking at NO2, I might as well look at methane. Why not? You never know. And we found a nice methane enhancements over the urban area. And so I looked here, you can see these 6 areas, Buenos Aires, Lahore, Delhi, Houston, Lagos, and Madrid, all have methane enhancements over the urban area. The magenta line is like the high population area. So Johan Massaker has just published a paper in this on Buenos Aires. It's the landfill here, one of the biggest landfills in the world. And you can see, I mean, it's clearly enhanced over the landfill, but it's enhanced over the whole urban area. Like, same thing for the whole, there's a landfill there, but it's, the enhancement is over the whole urban area. Once you get, methane is harder to observe than NO2. So you can see these other cities on the bottom, the data is noisier, like over Houston. It's noisier, but it doesn't really correspond to what current emission countries expect. But this is the zoom over Dhaka. We have a 20 ppb enhancement. So that, you know, given a background of around 2000 ppb, that's like a 1% enhancement. That's pretty small. A lot of people at the moment are looking at plumes of like ppm level plumes of methane. And so we're focused on point sources. this work is looking at kind of area diffuse sources over a long time period. So I thought, well, next step then, there's clearly something of interest here. I'll correlate it with the EDGAR, and we'll have a nice paper showing how great EDGAR is, but it could be even better, and then everybody's happy. And it turns out my correlation with the EDGAR emissions was 0. Just total noise, nothing. So I thought, well, I'll look at the sectors within EDGAR, nothing. So finally, I found a data set of, well, okay, I'm getting ahead of myself. So I thought, well, we'll look at how many cities can I find these enhancements? 61 cities have something that I deemed, subjectively speaking, could be a recognizable urban signature. There's 26 urban areas where there was a good, what I deem to be sufficient signal, but no enhancement, and 35 where there was just no retrieval. Mountainous, cloudy, forest, whatever. You see, we are, in fact, in North America, the bad guys of air pollution. We emit a lot. It really is true. The Europeans tend to be cleaner. And then here in South Asia, lots of emissions. But still no correlation with emissions inventory and things. So I found a wastewater production rate database. This group in the Netherlands has a CDF file with wastewater production rate. How much is produced, how much is treated, how much is untreated, released to the environment, how much is recycled. Get all this in a nice map. I pulled it all out for the 61 cities. And here you see these box plots for high-income countries. I've segregated the data. I've got my methane emissions here, kilograms per person per year. For cities that treat all their wastewater, and then cities that only treat most of it, up to cities that treat the least amount of it. And so we do this a lot. We have bigger storms than Europe, in truth. Our storms are much better than Europe's storms. So we have this problem with stormwater overflow, and it releases sewage to the environment. But in Asia, the correlation holds too. Cities that treat most of their water, their wastewater, have lower emissions than cities that treat less of their water. So we're pretty excited. This seems to show that there's a big source of methane that's been unreported at the moment. This is a summary table from the paper. The emissions from the TROPOMI estimates are like 3 to 4 times what they are in EDGAR. And if it holds, it could be like a significant portion of the EDGAR inventory. If we were to reduce them, hey, we could reduce our 61, just reducing the 61 cities, actually just reducing the 33 cities that are emitting a lot more to the level of the others would have a 2% drop in global methane emissions. I mean, from 33 cities, that's actually quite a lot. If we were to reduce all those 61 cities, we would have an even bigger emission. And then if we scale up and say, well, there's no reason these cities are different from any other 2 million person city, we've got 385 urban areas with more than 2 million inhabitants. They could potentially, if all of these cities emit as much as our average over here, 40 kilograms per person per year, that would account for 22% of methane emissions in the inventory. And if we were to treat the wastewater in those cities better, we could have a reduction of 10 to 15% of methane globally. So this is kind of interesting for, when I was in Dhaka, we met with the mayor of Dhaka, who's like this really gung-ho, let's get things done person. He's really interested in sanitation. He's really interested in climate change. He was like looking at this and all of a sudden it's like, wow, I could hit 2 birds with 1 stone. This is fabulous. We can be improving urban sanitation, which we should be doing anyway, and we would be improving the climate at the same time. So maybe that would create massive growth. So thank you.
Great, thank you so much, Ben. So our next speaker is going to be Brad Pierce from University of Wisconsin-Madison.
Did quite right. I hope the rest of the slides are okay. Okay, so I'm going to talk briefly about work we're doing in terms of using satellite data to support emission control strategies and talk about where I think we should be going in the future with new higher resolution, both temporally and spatially resolution data. Yeah.
Can you stand in the middle so the camera can see?
Okay. Okay, so this is a busy slide, but I'm going to spend a little bit of time on this. This is work that was done by James East and Baron Henderson, and actually grew out of one of the earlier HAQAST Tiger Team activities. And what they're doing here is they're using a finite difference mass balance inversion approach that was developed by Lars earlier on, except now we're using it within the context of a satellite data simulation system. So we're bringing in a full model prediction and a data simulation system, and then using that for this mass balance adjustment. These are results from, I believe, a 25-kilometer hemispheric CMAX simulation. And it's looking at the impact of using both OMI and TROPOMI to constrain NOx emissions in this hemispheric inventory. This figure in the upper right kind of illustrates the approach. Again, it's a standard mass balance approach, except for this step, which is where we actually, instead of just looking at the difference between, for example, a model and a satellite column, we're actually doing a data simulation and getting analysis increments and using those analysis increments to update the column. The other part of this that they developed was an iterative approach. So you go through this once, you get an adjustment, but because of the nonlinear NOx chemistry, that new emission actually still has a different response. And this is iterated about 5 times until you get very small analysis increments and therefore converged in emissions. So that's the approach. This is appropriate for kind of global scale modeling. But what you'll see here, and I'm not going to go into the details of here because you can see it quite clearly. OMI, you get basically positive adjustments in the emissions. TROPOMI, you get basically negative adjustments in the emissions. So we've got very significant differences in the response between TROPOMI and OMI. This is version 1.22 of TROPOMI, which has known low biases, but these low biases still exist in the updated version 2.3. So a key take home from this is that there is a really significant need to have efforts to develop robust and common retrievals that span different satellite systems. So in the future, when we've got both polar orbiting and geostationary measurements of NO2, we need to have harmonized retrievals so that the different satellite instruments and their results are not adversely or actually opposing each other, combined. And I know that at NASA there is, I believe through the Measures program, there's a MINDS project that is developing a uniform retrieval for each one of the polar orbiting. If you look at these results though, so these are opposing results over Europe. They're actually fairly consistent, at least in the winter time. And so this is not like this is a overall bias. This is differences in, there's different geographic regions. So, and interestingly enough, this figure here, first of all, this shows in the blue is the prior emission inventory. In the yellow or the orange and the purple is the TROPOMI versus the OMI adjustment. They go in opposite directions. And then here's 2 different emission inventories: CAMS, the Copernicus Atmosphere Monitoring Service, and TCR2, which is the NASA Tropospheric Chemical Reanalysis Product. What you'll see is that TROPOMI actually draws the a priori emissions very close to what CAMS has. So there's consistency in that. And the OMI itself draws it more towards the NASA thing. So again, there's large uncertainties in the emission inventories themselves with a fairly wide spread between different emission inventories, and using these satellite data products that have different biases results in, again, uncertainty in that. So that's a key point, key take home point. So where would we go next? So what we have now, and Ben's presentation looking at how you can use TROPOMI now with these flux calculations to really drill down and start getting information on the urban scale, we'll be able to do even more with tempo. particularly it has higher spatial resolution, but more importantly, it's got diurnal resolution. And we know that emission inventories vary significantly throughout the day. So this is a map. This is a map for Chicago. There's downtown Chicago. This is from the Neighborhood Emissions Mapping Operation, NEMO, which is put together by May and Tom. It's a 1 kilometer emission inventory that is for the whole continental United States. To me, this is unprecedented. So that now we have an emission inventory that's been vetted with EPA and developed with EPA that we can now use to look at urban scale emissions throughout the continental US. And in the same way that Ben was showing, what you can get in terms of source regions is spatial separation. And this is going to be key as we start trying to drill down even further in urban areas like Chicago. So here we've got downtown Chicago in terms of, this is NO2 emissions in moles per hour. You can see the various the freeway corridors, and you can see the airports standing out and even interchanges between different freeways. That's the 1 kilometer emission inventory. This is roughly the tempo pixel, 2 by 4.5. And so you can see that with tempo, we should be able to distinguish, for example, airports. Whether we'll be able to distinguish these roads is something that I think we'll need to see. You can see that with TROPOMI, you're beginning to be able to distinguish these interchanges, but it's that ability to look at spatial separation of these different sectors that's going to be a key to trying to understand and use these for emissions control strategies. So that's what the emissions inventory look like. And this is my last slide. What in reality then the NO2 column looks like at high resolution in an urban area, once you've done time averaging, the features align with the sources. There's some diffusion because of the different transport. But if you look at it on a snapshot, what you see is that the high resolution NO2 plumes that you see are actually downwind from the emission sources. And so for us, any sort of finite mass balance, data assimilation based emission adjustment, we need to be able to account for that plume resolving nature of the high resolution measurements. And we need to be able to track those plumes back to their source regions. So this is an example. This is geotasso measurements, 1 kilometer geotasso airborne measurements made by Laura Judd, Scott Jantz during the Lake Michigan ozone study. This is Milwaukee. Chicago is just south of here. And then this is a 1.3 kilometer CMAQ model simulation that is described in this this manuscript that's in review. And what you can see here, Milwaukee looks like pretty much a source region, but you can see these plumes here that are clearly blowing to the northwest. You can see a plume here that is the Oak Creek power plant that's blowing offshore. This is the Chicago plume. And so we need to link these measurements with trajectory mapping to actually identify what the source regions are. This is an example that we did during Elmos, where we initialized trajectories near the surface at the higher NO2 emission spots for both Milwaukee and Chicago. And we look at their transport over time. These are colored by the time that they were emitted. And you can see that we get this plume from Milwaukee that goes off over the lake and then wraps around and is transported towards the northwest, consistent with these. And you can see that the Chicago plume is again advected out over here and then towards the west. And that at a given point where we're observing that NO2 column, you actually have emissions from not only different source regions, but different kinds. And deconvolving that within an emission constraint system is what I consider to be sort of the next step in developing capabilities to use high resolution emissions, high resolution models, and satellite data for emission control strategy. Thanks.
Great. And our final speakers of this session are Lars and Leif Paulson from the Wyoming Department of Environmental Quality.
Well, good morning. Thanks for having us today. So we thought the best opportunity to explain what satellite imagery could do for us, we decided it'd be best to give an overview of our agency and some of the background about Wyoming. So first, Wyoming is a large state. It's the 10th largest state in the nation. It's got 97,914 square miles of land. With that, we're also the least populated with only 600,000 people overall. Our largest city, Cheyenne, has 67,000 people in it roughly. So not a very large population of people. But with that, we have a large industry, especially within the ministries or minerals industry. Our economy is based on three major areas: minerals, and of course, we know things like coal, natural gas, trona. Has anybody ever heard of trona? No, how about soda ash or baking soda? Yeah, anybody use baking soda? Yeah, we have the largest supply of trona in the world. We mine about 19 million tons of trona every year. And at that rate, we have 2,350 years worth of trona still available for us. Our coal reserves as well, we mine about 330 million tons of coal every year. And at that rate, we have about 15 to 1,700 years worth of coal in our reserves. So extremely mineral rich state. Agriculture wise too, we make large incomes there with barley, hay, wheat, sugar beets, livestock, and so forth. We have a lot of large fertilizer plants within our state as well. So our final area of economy is in tourism. So we have a lot of large places to visit like Yellowstone National Park and Devil's Tower and things like that. So we get a lot of tourism as well. But with that said, we're in a state that has over 25,000 permitted facilities in Wyoming. There's 110 Title V sources. These are gas plants, refineries, trona mines, power plants, etc. We have 30 synthetic miners, and then we have 25,000 miner sources, which are our oil and gas and so forth. Concrete plants, asphalt plants are just a sample of some of the many things we have. So we have a air quality division. We actually have our DEQ is broken into six divisions, and then our division air quality itself is broken into 6 programs. I'm the program manager for the compliance program. Leif is here with the monitoring program, and then we have our new source review, our Title V permitting, our rules team, and our air quality resource management, which deals with much of the emissions inventories. And so in my staff, thinking about the size of our state and how many facilities you have, you might think, wow, this is a big crew. Well, I have a staff total of 26. I have 21 inspectors across 5 districts in our state when I have a full crew, but right now I'm short 5 inspectors. So I only have 16 inspectors right now. And I have 2 in my enforcement team and then 2 on our asbestos staff. So if you think about the numbers, 25,000+ facilities and 16 inspectors, you can kind of see the ratios we have to deal with here. And then of course our monitoring program has 11 staff nominally, but I'll let Leif talk a little bit about those.
Well, thank you.
You're on.
Oh, thank you. Thank you, Lars. Well, a little bit about us. Yeah, 11 staff members, as Lars said. We have a few vacancies right now, but I'll get into a little bit about the AQD's ambient air monitoring program. We have 3 primary types of ambient air monitoring: SLAMs, which are state and local air monitoring stations, SPMs, which are special purpose monitors, and we have mobile stations. And just a word of caution when I say mobile stations, this does not entail staff driving mobile monitors throughout the state all over. By mobile stations, we typically, they have wheels and we park them at a location that meets appropriate siting criteria that we determine to monitor for a period of at least 12 consecutive months to explore ambient air quality at a specific site. We have a few options to view our data. So the first one I want to mention and plug for YBizNet. There you can see, and we can give you a little later on, business cards and other means to access these websites. But YBizNet has our continuous near real-time ambient air monitoring data. And the viz part of it, some of the stations on YBizNet have cameras that capture images every 15 minutes. In a few slides, might be a little surprise towards the end on that, so stay tuned. Open Air is an AQD data repository with quarterly and annual validated ambient air monitoring data and reports that document all the QA/QC procedures at each station. And please check out the AQD's Air Pollution Monitoring Program homepage to see our annual network plans and our 5-year network assessments for a lot more detail on each monitoring station. So I mentioned slams a second ago. Here's a map of them. And what we have here, the main purpose of these is for compliance with the NAAQS and population exposure. And I'll use the term loosely, Wyoming cities, given Lars mentioning the population a minute ago. But every one of these yellow stations you're seeing here, at a minimum, they have continuous PM 2.5. Here in the Southeast Cheyenne, where we're stationed at, this is our NCOR station, which has all the monitors associated with NCOR that the EPA requires. Jackson and Sheridan have continuous PM10 in addition to 2.5. Our special purpose monitors here, they're scattered throughout the state, and they have a variety of objectives. Some may be population exposure, like Casper, one of Wyoming's larger cities, but there are other stations that may have an objective of background monitoring or downwind monitoring. It just depends. And each station monitors for different pollutants. They may not all necessarily monitor for the same thing. And you probably noticed maybe this little purple area here. This is our upper Green River Basin ozone non-attainment area. We have 5 stations within here. And so what could happen during the wintertime months is we could have a combination from NOx and VOC precursor emissions, snow cover on the ground, sunlight reflection, and this unique topography with the mountains here can lead to the formation of ozone. And so we have 5 stations here that at a minimum continuously monitor for NO2 and ozone within the boundary of the non-attainment area. And finally, the mobile stations, we kind of see we've been everywhere throughout the state. Why do we go there? How do we choose this? Well, Lars or somebody from compliance may give a recommendation of a concern that they want us to monitor for. Other times it could be due to a finding in our network assessment recommending exploratory monitoring in a previously unmonitored location. And so at a minimum, our mobile monitoring fleet has continuous PM10, 2.5, NO2, ozone, SO2, and methane, non-methane hydrocarbons that we monitor for. So we are able to cover conditions, and we have 3 in the Green Kemmer, Riverton, and Laramie County active right now. And with that, I will turn it back over to Lars.
All right, so how much did you hear about satellites in all this? None, right? We actually don't use satellite imagery at this time. So when I say, satellite imagery is, the ceiling's the limit for us, no pun intended. It's really something that we're seeing could be very useful to us as a state agency. So, we definitely may be reaching out to people in this community to say, hey, please help us out with this, because we are kind of ignorant when it comes to satellite imagery, but see that there's a lot of potential to increase our capacity and capabilities with being such a small organization that we are. So, point being that satellite imagery is cool, and we look forward to using more of it. And this here is from our Boulder station. These are the northern lights that we actually got a picture of at our station. So that's kind of a little nugget. And with that, we'll stand by for questions.
Great. Well, thank you so much. Could we invite all of our panelists to come up? And Jenny, I'm realizing I think we need one more chair. Okay, great. Thank you.
It's true.
Great. Oh. So let's open up for questions and discussion. Let's see. Let Alberto go first.
Thank you. First of all, congratulations. This was a fascinating session. All the talks were just right on target. And I want to ask Ben a question, but also invite the others because I think any one of you could consider it. And our colleagues from Wyoming are the perfect segue. So when you compare satellites to inventories and you find differences, it's not surprising to me because we know that emission inventories rely on a significant number of assumptions. And they also rely on 100% compliance with rules and regulations through permitting programs. So my question for you, Ben, would be, have you considered taking the type of approach that you have taken and look further and deeper to see, it's not surprising that you're finding differences. Now the question is, why are we seeing differences? And if you start to look at the sources and the permits that apply, that may be an interesting area of research. I don't know if you can offer some thoughts because again, you know, the rules and regulations say one thing, the real world, as we found out with the Volkswagen case, is a different animal. Is that something that you will offer some thoughts about?
Thank you for the question. You know, I'm a data analyst. Personally, I started in modeling and I do this. And I think we alluded to yesterday the academic publishing game, you know, and it can be kind of hard to say, oh, I can do this cool thing and I can publish it once for one place and I can't publish it for all these other places that I might want to look at. So I'm hoping that people will pick up on my paper and, you know, like all of us, we're hoping that it kind of goes through this kind of cycle of things, but it's kind of a gradual cycle. So I think it's good to have programs like HAQAST to bring people together, hopefully so that there can be a faster development cycle of people working in different areas, just kind of collaborating. And certainly this whole geospatial science is exploding at the moment. So there's tools now, there's kind of a convergence of tools where we can talk to each other more easily than maybe we could in the past.
I'll maybe add to that a little bit. So we're working again through the NASA Applied Science Program. We're working very closely with the Lake Michigan Air Directors Consortium. And so we are now having exactly that same conversation that you're bringing up, which is, yep, you've shown that there's differences. We need to know where errors in our sectors are so we can do that. And with this, particularly, you know, the airborne geotassel measurements for us that's the view of the future. And the LADCO emission developers are looking at that in detail and seeing hot spots there that they can say, this is railway. And we have uncertainties in our railway emissions. And I think now we can start drilling down to sectors. But you do have to have high enough resolution data at an urban scale so that you can actually spatially separate those out. And so that is certainly the next step. And I think that particularly with tempo, because again, the emissions have various different diurnal cycles too, and we'll be able to add more information to that.
Yeah, so thank you all so much. This was a great session. And my question is following up on Alberto's, but especially to Annie and Lars and Leif. This idea that, you know, just like Ben mentioned, I mean, scientists write a paper once and then it's publishable and then they're moving on to a new project. And the flux divergence method that was presented here could be applied everywhere. And yet Ben cannot personally apply it everywhere. And so, you know, there's different, we talked about this a little bit yesterday. I mean, of course, there's training programs, but there's so many advanced methods, and even someone who knows how to use data and tools for like NASA Worldview or tracking trends it may not even be a good use of your time, just like it's not a good use of his time to do flux divergence everywhere. It may not be a good use of your time to learn flux divergence. And I guess what is the right way to pass the ball to get that like broader implementation? And I feel like consulting companies play a role. I feel like training plays a role. And I'd be curious about all of your perspectives on like, how do we get these cool ideas that could be useful and actually make them broadly useful?
Thank you for that question, Tracy. It definitely gets to the heart of a lot of issues that we have in science, right? That's something that I definitely love about working at a consulting company is the opportunity to dive deeper into these developed techniques that academic researchers have done and connect those to often our clients that are different DEQs for the state or the county level. So we do definitely get an opportunity to use those methods, and we benefit from being here and learning about these different techniques that we could use. So I do think consulting and government work is really where we can make that connection. I think something interesting about your work, I didn't hear how integrated over time it was. So we have increases in emissions from methane. Is that maybe due to super emitter events? Or is it an overall higher emission at all times? Kind of getting to Alberto's question, is this because emissions inventories are bottom up reported for regular operating procedures? I think a lot of the literature tells us that particularly for methane emissions, there's super emitter events that are infrequent and unexpected. And if you aren't constantly monitoring, you can miss them and they'll have high impact. So yeah, I'll give it to my colleagues in government about regular monitoring and the use of the system.
Yeah, so we think that consulting is a great way to get this information passed on. Obviously, with a small organization like we have and the trouble we have filling positions, if we go up and say, hey, boss, we want to add something new to our program, it's usually frowned upon, so getting assistance is a key part to it, but we've seen a need for it, definitely. We recently did have a company emit for a safety reason some gas because they had high O2 concentrations in the gas stream, and they weren't able to reduce them enough to actually continue processing the gas, so they had to vent that gas. And so the satellite imagery we did receive from it painted a much different picture than what they did, and they also had fence line monitoring that showed no exceedance or increase in the values. So there's a little bit of a disconnect between the fence line monitors as well as what the satellites are seeing. And so us learning and kind of getting our hands wrapped around that's something new for us to do. So we see that there's huge opportunity to work with industries as well as with consultants to get a better picture of what is truly going on. So.
Okay, just give a brief shout out to Libby Moore on what she showed yesterday and Environmental Defense Fund. I'm working with people at World Resource Institute and the environmental organizations that increasingly are having they're hiring their own scientists and doing outstanding work.
My question is for Dr. DuBois on the flux divergence and especially for the methane. I was highly interested in your Houston retrieval, and you said it was noisy, but we've done mobile measurements in a car and we're finding leakages in the infrastructure. So I was curious whether or not do you believe the method could be used to extract that fine a scale where you could get to relatively small overall, yeah, there's leakages in the system, but we can actually pinpoint somewhat larger leakages in the system, subcritical, it's not going to explode, but these are leakages that we're finding in the system itself. Could that method be used for that? And is that noise that you were talking about potentially that?
I think with TROPOMI methane, we're kind of pushing the boundary. The TROPOMI NO2 retrieval is much more robust than the TROPOMI methane. And so, because I went through and I looked at landfills, for example, well, maybe we can pinpoint landfills. And it's really kind of a little shaky. So I think we've reached with this current satellite, and hopefully there will be, future generations of set. I mean, there are the methane set PDF is sending up.
I would maybe add that I think that airborne measurements can fill that gap pretty well using high resolution, visible and infrared imaging, get down to infrastructure types to see leaks like that. So don't forget about the airborne measurement.
Great, Doug? Yeah.
Oh, Arlene, we have a question online. This one is for Brad from Michael Geiger. Will you be conducting high resolution modeling over NYC during the AGES study this summer? He says tempo may have first light by August, so it should be available.
Good question, and yes, we will. So the pulling together the NEMO emission data set is actually so that we're ready for the AGES campaign next summer. And we'll be doing real-time forecasts at about 4 kilometer resolution for Chicago and New York. And then my graduate student, Gerald Octon, will be doing high resolution post-mission analysis certainly for Chicago. And we can talk about doing the same thing for New York.
Great, thanks.
Hey, Doug Boyer from TCQ. Annie, I'm interested in the VOC NOx ratio work for ozone events that you showed. And have you submitted those for the state? And did you have any feedback from EPA? I'm also thinking about what Brad showed and how some of the recirculation patterns can bring in, say, 2 plumes together with different times, and how all that works into an exceptional event case, and if there was any feedback from EPA.
We have not submitted it yet, so we haven't gotten any EPA feedback just yet. Definitely Arlene's group has done a lot of the foundational look at this ozone sensitivity. But I would say that one of the nice things about this technique, which we mostly got from the Jin et al. Paper, is that you're using a non-dimensional analysis. You're taking the VOC to NOx ratio, and so you can move away a little bit from the absolute concentration issues and have a better eye towards trends. So it'll be really interesting to see if we do get feedback on that from them. We don't always get a ton of feedback, and they are quite difficult to get exceptional events passed, but stay tuned for sure.
Hi, so there are like a number of very impressive kind of technical accomplishments that you presented. Often seeming kind of probably having like pretty intricate workflows to do them. And I was wondering if you can kind of talk about what are the bottlenecks that that are kind of like the things that are keeping you from doing more, or like what kind of support could you have, in terms of, I don't know if it's, software, hardware, or kind of data transfer or something else that if you had it, you would be able to do even more.
So I think this kind of gets back to the question that Tracy raised about, scientists doing a publication and then moving on. And I think that is where the applied science program really fits in. The work that I showed, where we're using, data assimilation within this finite mass balance approach, was funded by HAQAST, and we transferred that capability to EPA. So then it has sustained effort. What that took was a lot of technical interface with people within my group and people at EPA to accomplish that. And that's important. That takes some time. The high resolution modeling work that I was showing at the end is also from the NASA Applied Science Program. And again, it was us working over 3 years with LADCO and the LADCO modeling team to develop kind of an optimal configuration, and then transfer that to them, where they actually took that and put it in an AWS system. So they took our modeling framework and then were able to put it in Amazon Web Service and did an entire year at 12.4 and 1.3 kilometers for the LADCO region. So you'd need to identify, partners on the stakeholder side that have that technical expertise. it's often not going to be the state agencies. I see, this real importance for bringing EPA into it so that there's some sustained capability. For example, doing the mass flux work, that's something that I think could be transferred and EPA could then share that as a community resource. And so those links with the regional planning offices that support the states and links with the EPA, I think are the key to accomplish that.
So I'm going to jump in with a question, if that's okay. And I think building on Chris's question, I was particularly curious to hear from Annie and Leif or Lars from Wyoming, or both of you, about sort of what, if you have kind of a wish list of what satellite data would ideally help you with. And so I guess in the case of Annie, I'm curious with your community groups, like what are the air pollutants that you're looking to monitor most, or that you get asked about the most? And is that information that satellites can help provide? And then I guess for Wyoming, I heard about, sorry, it doesn't matter, but wintertime ozone events, which I think are particularly challenging for satellites when you've got snow cover. And so, but on the other hand, summertime wildfires, I think there's more promise there. So anyways, just sort of trying to see maybe a little more broader discussion across the panel on what are your needs and where's the intersection maybe with where the current or almost current satellite data are.
So I guess I have two ideas that came to mind while you were talking. One of the most common community pollutants that we have concerns about is hydrogen sulfide. And I really haven't looked into satellite data for that at all. That's been enough of a struggle with the ground monitors to get reliable data. So that's something I haven't looked into at all, is if we could look at hydrogen sulfide. It tends to be a very big community problem, and it has a low health threshold. So concerning. And then for the ozone, yes, the winter is definitely a struggle. You have increased cloud cover and potentially a clear sky bias in the data when you're even looking at it. Something that I saw in my work with the TROPOMI NOx VOC ratio is that, well, during summertime wildfires, we would see this increase in that ratio. I was also finding fire days in the not wildfire season, so presumably prescribed burning. And they seem to have somewhat different impacts on the TROPOMI ratio as well as on ozone influence. A lot more work needs to be done there on teasing out the meteorology of that. Is that because prescribed burning is different than wildfires, or is that because the meteorology and the planetary boundary layer is really different in the winter compared to the summer? So I think a lot of our communities will continue to have questions with prescribed burning, especially for us with California's Central Valley. Those are big concerns.
Yeah, I would say that wintertime ozone is a big issue for us. For about the last 10 years, we've been asking EPA to help develop a model for us so we can try to model some of this more. And they're just not interested. We're not that important to them, I guess. So we've been doing a lot of work on our own. That's one of the reasons we have 5 monitors, ground monitors in that area alone, just to try to figure out what's happening there. So we think ozone, hey, it's got to be a nice hot day and everything else. Well, we get a sunny day with negative 10-degree weather and we'll have an ozone formation. So it's, kind of unique circumstances around it. So if there could be development there, that'd be awesome. And along with wildfires, we probably have around 35 to 40 submissions annually regarding exceptional events related specifically to wildfires. So, and the EPA has got some pretty specific requirements to submit those, and satellite imagery is something that would really help us, be able to show how that's transitioned and how we've been affected by the smoke from some of those fires. And at least got
Just ask, are those PM and ozone that you're submitting?
Yeah, 2020 and 2021, we had summertime exceedances for PM 2.5 and ozone, correct? Presumably due to wildfire smoke. Targeted training in the satellite realm would be very beneficial to us as regulators who, it's fascinating. We just don't spend enough day-to-day time in this. in this realm. And as Lars mentioned, just the staffing challenges of a small agency and would certainly help us to learn and start to speak the lingo and find applicability for an exceptional events demonstration or other purposes.
And on the wish list. So on the wish list topic, I think personal experience I've had is that there's so much available from NASA RSAT, and you go to the training that's available, and I end up bookmarking like 18 different trainings that I want to do. It would be really great if there was like a 1-hour YouTube video or a sample coursework, like, hey, you want to learn about different ways to look at PM 2.5. Here's our recommended 3 courses plus a 1-hour or 30-minute overview to help people get organized and started. Because even for me, someone who definitely has the technical skills to learn it, the time that it would take to get organized and stay on topic could be a little bit barrier.
So a roadmap to existing resources. Great. Okay.
I also have another wish list on top of what we have been discussing. And I believe what Annie mentioned is like a curated learning pathway. I think what we can learn from, as an example, is like Esri. I'm not really advocating or anything, but the ArcGIS itself has a lot of modules and everything. So they have even curated multiple pathways to go through. So that might be a good example to, I guess, look into. In terms of transitioning from sort of basic research to the application, one thing that I think will be very, very helpful is for the funding agency to consider some lot of money as a kind of packaging as part of the project, so that by the end of the research project, with some code or tools that developed, coming up with some example that's kind of applicable for certain stakeholders, but that's actually part of the project delivery, so that if it is shared through the GitHub or anything with an example, with some manual, that would be very, very helpful. For that part, the really good example that I think is Rambo's effort to put very detailed manual for the chemics, because they don't necessarily run any training really. I guess they have on-demand training, but majority of people that I know that they run chemics is learning from their example files and manual. That's just sufficient enough for even beginners to follow. So I think however, like I said, that the really challenging part is at the end of the project, you don't necessarily really have time to write the manual for a little broader users, because believe it or not, that takes a lot of time actually. So I think it's geared toward my wish list to the funding agency to consider that part as actually part of the project. So hopefully that kind of smooth, make a smooth pathway from the research to the application.
I guess I'd just like to broaden the scope of the discussion a bit. Do folks in this room find hourly data from ground monitors as sufficient for all of, I know we're talking about satellites, but we're trying to connect this to the ground too. Are the hourly databases that are reported from the states adequate for all of your needs? And I ask that because states are usually collecting data at a far, far, far higher temporal resolution. And so I'm curious as to whether or not that would be valuable to scientists in this room or whatever. And then if the answer is, if it's potentially yes, states have issues with reporting that data, is that something NASA would be interested in hosting if we were to give you minute level data, for instance?
So as a user of the AQS data, I would say that, and in particular in a lot of coastal environments where we're looking at lake breeze and sea breeze and bay breeze circulations that evolve over, minutes timescales. When we when we get AQS data from field campaigns, we're getting 1 minute data because we need that resolution. So for example, during the LMOS campaign, state of Wisconsin, state of Illinois submitted 1 minute data to that NASA field archive data. And so for a campaign, that was the appropriate place to do it. I don't think NASA is the place that should have high resolution data for all of CONUS. But I think that is something that it'd be important to raise, with EPA, because there is a lot of cases where, we saw that dust gust event, I don't think, maybe that was 1 hour data, but we do often need much higher resolution data.
So I'm asking here because I've actually raised this with EPA before about trying to get a system in place to load higher resolution data. And that was many years ago. And it kind of just, it was a ghosted idea. So I'm asking it again because it seems like it potentially is relevant for some of these campaigns, especially if we're getting PM 2.5 now that's continuously monitored at some of these locations at minute resolution. And I know at campaigns, the PIs will be getting that, but if there's someone else that wants to investigate, can they just pull it from an HAQAST database? Probably not, maybe a NASA database. I don't know if doesn't sound like it's a NASA host interest, but if there is interest in that, maybe we should talk about how we can make that collaboration available.
Okay, final burning question. I see two.
Yeah, and this is a great topic.
Aaron and
We don't have.
Yeah, thinking about tempo a little bit on your topic there, we're going to have that sub-hourly data for tempo on the east and the west and our special observations going on in that mission. So like that would be another way we can have that minute, higher temporal resolution ground-based data. That'd be really awesome if we can push that forward, in my opinion, from the tempo perspective alone.
If NASA wants to talk to EPA with
I've been
me,
on.
I'm all for it.
So maybe one comment on that. Again, when we got 1 minute data, we got it from the state of Illinois and the state of Wisconsin. And that it may be that it's partnerships with the state agencies. It's probably going to be the most efficient way for you to get that kind of data.
Mine is quick.
Amber, okay, yeah, Amber can close out our session.
So just listening to all of you, this is not only to the panel, but to people that have control in states. We're talking about exceptional events for fires. And I hear anecdotal ones when people call and they want to know how to use particular satellites and frustration over events that are not approved. Could you give me a sense of about how many are put in? You gave a number, but how many are not approved or approved, either way you want to look at it? I mean, just because I really have no sense of that.
Oh boy. That's an interesting question. The process in 40 CFR 5014 requires, regional concurrence from your EPA office to approve them. We're just in the process right now of analyzing the 2020 and 2021 data. We've not yet submitted demonstrations to the EPA.
Ever had an exceptional event approved? Like
Yes.
most of them that are approved.
I'll have to talk maybe offline on that. I don't want to give any wrong info, but I can.
I can maybe say a few things. It really depends. For us, our clients have a say in which ones we apply for. And we recommend them to use caution because the EPA examines them in bulk. And so if you submit 20 and they find one that they disagree with, they will not even read the other ones. So we try to encourage them to only apply for the ones that are really clear, clearly an exceptional event. So yeah, for example, this year, I think we are applying for 8 exceptional dust events for a 3-year period. I just joined the team this year, so I know last year their package that they submitted was not approved. So something like 10 that they submitted, and the EPA came upon one in that 10 package that they could not agree with, and so that entire package was submitted. I did hear anecdotally that I think CARB submitted in California and had a package of maybe like 20 approved, which was huge, a huge number. Everyone was talking about it. I think a lot of those were in 2020, which was an exceptional wildfire season. But I would say that it's exceedingly slim chance of getting them approved. And the fact that CARB got 20 approved was very noteworthy.
Great. Well, I just have one announcement from online about our set training sessions. And they currently have an overview training. Is this for PM 2.5? I'm actually not entirely clear, but it sounds like it comes in 2 1.5-hour videos. So maybe we can make that information linked to HAQAST tools and resources. All right. So with that, thank you so much, everyone, for a fantastic discussion. And